So this is our last video with vector valued functions. Okay, keep in mind, just like the others, you don't necessarily have to write all of these down. When we get to formulas, I would say maybe write those down so you have them for the practice problems. But because you could always reference back to the video, you don't need to necessarily write everything down, just kind of follow along. So the first thing is derivatives of vector value functions. Pretty basic. If you have r of t as this vector valued function, the derivative r prime of t is just the derivative of the individual parts. So if we have r of t as e to t, e to 2t, its derivative down here would just be e to the t again and 2e to the 2t. Okay, so pretty basic for finding the derivative. Um, Now, what is that derivative telling us? It's telling us um, the direction and the steepness for that derivative vector, and we can also use it to find the speed. So in this picture here, our initial position at 1, if I subbed in 1 into the r of t, you'd get e and e squared, and that's giving you this point right here. Well, then the derivative, if we stubbed in 1, we'd get e and we get 2e squared. So that's about 2.71 and 14.71. So to draw in the derivative vector, we'd go the 2.71 to the right and 14.7 up. So it shows us at that instant the steepness that you're traveling. It tells you the direction you're traveling at that instant. And we'll see in a second the length of this vector here is actually what will tell us the speed at that instant. So here's another example. Say we started with sine t cos t. So your derivative would just be cos t negative sine t. And at pi over 4, we'd get square root of 2 over 2 and negative radical 2 over 2. Well, in the original, if we had put in pi over 4, we'd get radical 2 over 2 for both of them. So our position is here in the original. So then if we plotted this, we're going right and then down the same amount. So that would be our velocity vector. The length of it, again, we will see in a second, would tell us our speed. So a vector value function is said to be smooth if the derivatives of each of the parts are not zero at the same time. So for this vector valued function, we want to see when would it be considered smooth. So we'll take the derivative of it, each of them doing a chain rule. And then, because they both have sine and cos, these are both going to be 0 anytime we're at the multiples of pi over 2. So our nice values, 0, pi over 2 pi, 3 pi over 2, and so on. So we're smooth everywhere, so on all real numbers, except when t is an n pi over 2, where n is an integer. So integrals, pretty similar idea with definite integrals as with derivatives. If you want to do the integral of r of t, you just do the integral of the individual parts. So we wanted, in this case, we're going to do this one from 1 to 4. So we're doing the individual integrals from 1 to 4 of each of the parts. So just take your antiderivatives, you sub them in, and then that gives you your integral. So we have 14 comma 18. Now, what does that really mean? Well, say the original vector value function r of t was a velocity. So now t is representing a time. That 1418 is telling us the displacement and in which direction. So it's telling us our vector we moved 14 units to the right and then 18 units up. Now your overall displacement, which will also be considered the speed, is if we just did a Pythagorean theorem with that. The speed notation, or it can be considered the magnitude also with vectors, is the double lines. And if you did the Pythagorean theorem, we'd get square root of 520. So that's the overall displacement just directly, and that would give us the speed. So here's a few formulas. These you can write down. So you got your velocity. You're just taking the individual derivatives. So I'm going to jump down to the bottom. The acceleration then would be the second derivative, so it shouldn't be any big surprise there. And then the speed, you're just basically doing Pythagorean theorem with the velocity vector, because that will allow you to find the actual length of that vector. So if you need more time to write those down, you can pause it, but I'm going to keep going. So say we have this original vector valued function. We want to find each of these things at pi over 4. Well, the original position, just sub in pi over 4. They'll each give you a square root of 2 over 2 times the 3, so we get this. For our velocity, we'll take the derivative. So here's your derivative of each of the parts. Then at pi over 4, those are each square root of 2 over 2's. So in our picture here, here's our initial position. And then we've got to go right 3 square root of 2 over 2 and down 3 square root of 2 over 2. So that's telling us the direction. The length of that would be the speed. And that's what we're going to find in part C. So if we do the square root of our first part squared plus our second part squared, those are like our legs. If you thought of it like a right triangle, doing that out will give us our speed. So our speed at that instant is 3. And then the acceleration, if we take the derivative of the r prime one, we'll get this. And if we fill in the pi over 4, they're just both negatives. So the acceleration vector would look like this. And what that's representing is it's the pole of the object. It's the change that's about to occur at that instant because it's going to pull in more. So that's your acceleration. Just another example doing those same things. So our position, if this is our original vector valued function, if we sub in 1, we get e comma 0. So here's our initial position. Take your derivative, sub in 1. So we're going up right 2.7 and up 1. So there's our vector for our velocity. The length of that would be the speed, and that's what we're finding in part C here. And then the acceleration vector, if we take another derivative, we get this and sub in 1. So we get e negative 1. So from our initial position, we go right 2.7, down 1. That's our acceleration, and that's representing the pole at that instant. So where is it going to head next, essentially? So let's say we're given an acceleration vectored value function. The particle's starting at this position at rest, and we want to know where it is after 2 seconds. So two things that we know, our velocity vector has to be 0, 0 when that's t equals 0 because we're starting from rest, and our initial position is negative 1, 3. So starting with this, we can take the antiderivative, and it'll give us the velocity. We've got our constants here. Well, we have 0, 0 when t is equal to 0, so we can set up two little equations and find those constants are just 0. So this is our final velocity vector valued function. Then for the position, take your antiderivative again. You've got your constants. We'll sub in 0 for t and negative 1 and 3 on the left. Solve for your constants. And this gives you then your position function. Well, we wanted to find at t equals 2, so if we sub in 2 for the t's, we get that as our position at t equals 2. And one last thing to note, if you ever had to find the length of a planar curve, it is the same as the arc length formula in a parametric curve. So you do the integral, you do square root of your x part squared plus your y part squared. And so just so you can see an example of that, so say this is your vector valued function. We want to find the length of this as it goes all the way around. So you got 0 to 2 pi, you got square root of the derivative of the first part squared plus square root of the derivative of the second part squared. If we square those out, we can pull out a radical 4, which just becomes a 2. This is just 1. Do your antiderivative and sub it in, and we end up getting 4 pi. Okay, so your length formula for vector values is exact same as your length formula for parametrics.